1 is just reminding you of some algebra and how we combine functions. All right, so it's the arithmetic operations, which arithmetic is adding, subtracting, multiplying, dividing functions, which also kind of goes hand in hand with function notation. And then we'll add compositions, which are not really an algebraic operation, but it is a unique operation to functions, and it's an important operation. So we're going to look at all of these kind of ways we combine functions. Any of the complex functions, if you go back and look at, in chapter 4, we did a whole bunch of complex functions, polynomials, rational functions, and power functions. All of the complex functions really are a sum, difference, product, quotient, or composition of two or more functions. Most functions are built up of smaller, simpler functions. An example, 4x minus 10 is a linear function. If you want to think about it, it's the difference of two simple functions, say 4x and 10. Right? The line 4x and the constant function 10. Right? We subtract them to get the new function 4x minus 10. All right, and so we're going to look at, again, this should be a fairly quick and easy review. It's just the way we can combine functions. All right, so the first one's the sum and difference, adding and subtracting. And the biggest thing with adding and subtracting functions is make sure you can only combine like terms and be very careful with subtraction. All right, so I've got my two functions here. F is x squared minus 5x and g is 2x minus 10. We want to find the sum, so that's should be a sum. That should be a plus there. The sum of those. Alright, so I want to find f of plus g of x. And so it's just take f of x and add it to g of x. So x squared minus 5x, add to it 2x minus 10. I put parentheses, although when we add, I probably don't need them, but I do that so that I remember when I subtract that it is going to be important. Now, collect like terms. The only like terms I have are my x terms. And so the sum of f plus g of x is x squared negative 3x minus 10. And there's my new function where I've combined f and g by addition. Now I'm going to do the same thing, but now I'm going to subtract. So I'm going to do the subtraction case. Alright, the difference. Difference means subtraction. So f minus g of x, and this is where the parentheses are important. I take my first function, x squared minus 5x, subtract the second function, 2x minus 10. This set of parentheses is vital because it reminds you you have to multiply through, distribute that negative. Now the first set of parentheses, you kind of can drop them. There's a 1. This is the set that's important. So I distribute my negative, so I get negative 2x. Negative times the negative 10 gives me a positive 10x. And then again, the x terms are the only like terms I have, so x squared minus 7x plus 10. But a common mistake students will make, and then it'll be wrong, is forgetting to distribute that negative. And so they'll get x squared minus 7x, and instead of plus 10, they'll do a minus 10. So make sure you're very, very careful with that. That's, again, the biggest thing with the difference is making sure that you distribute that negative and then collect like terms. And be very careful with collecting like terms. All right, the product of two functions. All right, the product means multiplication, so we multiply two functions. All right, it's just, again, take function f, multiply it by function g. All right, so for the following functions, we're going to find f times g, solve it for at x equals negative 1, and then I want to give the domains of the final solutions. It really has to do with the original functions. Alright, so f times g of x first, and then we'll plug the negative 1 in. Alright, it's just taking x squared minus 5x times 3 over x plus 2, which you could leave it like that, although it is simplified, and I don't know how picky the WebAssign is, or the MyLab is. But when we simplify across the top, the only thing that you can do is really multiply across the top. So this is 3 times x squared minus 5x divided by x plus 2 would be, and again, if you wanted to distribute your 3, you can. I probably wouldn't. And so before I go ahead and find the value for negative 1, I'm going to go ahead and find the domain. So the domain is everything except where this division will give me out a 0. Now if I plug a negative 2 in is what I can't have. So my domain is every x such that x cannot equal negative 2. Or interval notation would be negative infinity to negative 2, break at negative 2 to positive infinity. All right, now I'm going to find f of g of negative 1. So I'm going to take negative 1 and plug it into that new equation. So 3 times negative 1 squared minus 5 times negative 1 all over negative 1 plus 2, and that simplifies. Making sure you're very careful when you square this negative here. You've got to make sure that it's going to come out positive 1. So up top it's going to be 1 plus 5 times 3. So I get 18 over 1, and so 18 is the answer. All right, the next example. All right, this one's a little trickier. The domain part's a little trickier. The simplifying isn't too bad. I'm just going to leave it because I think it's just easier to do that. So g times f is just square root of 3 minus x times the square root of x plus 1. And you can't simplify that because they're not the same expression underneath, right? I can do square root of x times square root of x because I've got x values under that are the same. Well, these are not the same functions, right? 3 minus x is not the same as x plus 1, and so you can't simplify that. You can't combine those. So that's as simplified as it gets. So again, nothing to simplify there. I'm going to do the x equals negative 1 later, because I'm actually going to see if it is even in the domain. The domain of this is the hard part. All right, so the domain is, well, I've got two root functions, and really what it is what's the domain of both of these where they overlap. All right, and so remember, roots have to be positive, right, underneath them, because I can't have imaginary numbers. So my 3 minus x has to be greater than or 0, and at the same time, my 1 plus x has to be greater than or equal to 0. Right, and those have to solve, and again, then we'll combine them and see where they overlap. And so the first one is negative 3 moves to the other side, negative x greater than or equal to negative 3 divided by my negative 1. Remember, when I do that, I've got to flip my sign. So x has got to be smaller than positive 3. And x has to be bigger than negative 1. And so my domain then is between those two numbers. X is bigger than negative 1, but at the same time smaller than number 3. And so the domain in this case means I'm between every x such that x is greater than negative 1, less than positive 3. And so I can plug negative 1 in because it is in my domain because I have equal to it. And you can always check your graph. If you actually graph this, it comes out to like a semicircle shape between negative 1 and 3. And so it is, you could check it graphically if you wanted to. Or you could test points. Right, I know I have a 0 at 3 and a 0 at negative 1 and test them. You can do that as well. It comes out, does not exist over here. So it'd be negative, positive, negative in the different cases. All right, so there's the domain. That's the hard part. And then the last thing is then find it. So I'm going to find f of g of negative 1, which comes out to be 3 minus a negative 1 times 1 plus a negative 1, which this is where it zeroes out, right? I get square root of 4 here, but square root of 0 is fine. That just means it's 2 times 0, which comes out to be 0. So f times g of negative 1 is just 0. All right, we'll stop there. We'll pick up the quotient rule. Actually, maybe I'll just go ahead and do the quotient rule. All right, we'll do the quotient rule and then stop after the quotient rule. All right, the quotient rule is division, right? The quotient of two functions is when I take one, and so all of our rational functions were this case, all right? Whenever I took a polynomial divided by a polynomial and I got a rational expression, it involved this quotient rule. All right, so the quotient rule is I take my function f divided by my function g. The domain is everything that's in the domain of the original function, f, and the original function g, and the divisor cannot be 0. So there's actually 3 domains I have to check. F, G, and then my final answer, I can't have division by 0. All right, which is actually the catch in the second case of part A. All right, so I'm actually going to do my work here. I'm going to hold off on B. I'm going to kind of do A first. So we'll do A first. So f of x divided by, or f divided by g, f divided by g of x, which again is just f of x divided by g of x. So f of x would be x squared minus 5x divided by 3 over x plus 2, which that's an improper fraction. You don't leave improper fractions. So If you recall from algebra, division is the same as multiplied by the reciprocal, and so this is exactly the same as taking the x squared minus 5x and multiplying it by the reciprocal of this. Well, the reciprocal of that would be x plus 2 divided by 3. And so f divided by g of x simplifies to the fraction x squared minus 5x, x plus 2 divided by 3. And so the final expression is this denominator is never 0. But, so this checks, there's not a single place where the denominator gives me division by 0. But I do have to check the original functions that I use. And it kind of go back to here. I have to go check in what I originally used before I manipulated it algebraically. And this original expression does have a place where we can't have division by 0. And so the domain of this, even though the final answer comes out all real numbers, because of what we started with two separate functions that I combine, the domain is actually all values such that x cannot equal negative 2. What would happen here is there's a hole in the function there. Right? And so again, I have to check three things. My final answer, do I get division by 0? And in this case, my final answer, there was no number that I could plug into the final answer that'll give me my division by 0. But then I always have to check my original functions. Now, the original f was fine, but the original g had a division in it, and so that would give me a place where I could have division by 0. Alright, and so that was the catch in that one. Alright, now we'll do b. Alright, so my function b, so both of these, the check in the first case is fine, all real numbers, right? These are polynomials, domain of both have a domain of all reals. Alright, so I only have to check my final answer in both these cases. And so this is actually going to give me a rational function. It's a polynomial divided by a polynomial. And so I'm going to get a rational function when I take f divided by g of x. And so my f of x was the cube, so x cubed minus 3x squared plus 2x minus 6 divided by x minus 3. And so the domain in this case would be all of the x minus 3's, whenever I get division by 0. And so x cannot be 3. And so my domain is every x such that x does not equal 3. And so that was a case where the final answer was the one that gave me the division by 0. The first case was it was my original functions that gave me a division by 0. My final answer actually did not. Right? But you do have to check all three places. All right? So you have to be careful. Division's always the one where it gets a little trickier. Alright, so you have to be a little careful because nowhere in my entire function from beginning to end can I have division by 0. So I have to check everything, the beginning and the end. Alright, we will stop there and we'll practice these in a graphical example, I believe, in the next video.